Okay, just want to put a short video together to kind of help with the last phase of the course since we're kind of at week's end and the course actually ends next week. So by now, hopefully, we're working on Betty's Bats. Today is the 20th. The last date of the semester is the 27th. So I just wanted to put up a little bit of a video that I was going to do last week that we had some internet issues, so I was not able to sign on to Zoom. So let me try and share screen with a couple of things. I want to start with the idea that if you recall, we were really looking at, let me just pull this up. We were looking at Betty's Bats being, okay, being divided into basically three areas, and the production sheet is on the contents section or in the contents section of Blackboard. And really, we have three areas. So if you look at the first area relates to forecasting, which is the first thing that we did in the course. And, we had some PowerPoints and videos or video to that effect. And we learned that, among other things, forecasting was, in a sense, guessing what might occur in the future, but basically we were looking for forecast numbers for something. Forecast numbers for demand, forecast numbers for sales, forecast numbers for whatever it is we happen to, want to be searching for. And we realized that being a forecast, it's likely not going to be accurate in the sense that it's not going to produce the actual demand outcome, because we'll know the demand outcome, for example, in the cases we were using at the end of the period. But in advance of that final demand outcome, we're always trying to guess what we need to do towards the end of how many do I make, how many do I buy to resell, how many do I inventory, how many patients do I schedule, whatever the issue might be. So in Betty's Bats, the first area that we're working with is this idea of forecasting. And what we're trying to do is forecast the next year's production of Betty's Bats. So whatever year, because again, this is a classroom example, so it's not really an engineering outcome we're looking for. But if we were to take the first year, Betty's Bats, this fictitious company with a fictitious product, made 875,000 bats. Second year, they made 920,000 bats. Now, these are actual demand numbers that we were able to, as the producer of Betty's Bats, we were able to acquire at the end of the production year. So at the end of the year, we realized we did 875,000, end of year two, 920,000, end of year three, 1 million, year four, 950,000, and so forth. So we're now at the end of year five, and we just realized that we made 990,000 bats, and we're trying to forecast what we ought to do for the next year, for year six. That's our something less than practical example. So what are we going to do? Well, we're going to forecast. How are we going to forecast? Well, we learned in our forecasting examples for the course that there were a bunch of different things we could do. One of the simpler techniques was to simply do a 3-period moving average. Now, in the examples we used for the course, it was monthly. So we had 3 MA, 3-month moving average. We could do the same thing with days. We could do the same thing with years, etc. One technique would be to do a 3-period moving average. One of the underlying things we learned is that we rely on more recent data. So which 3 periods would we use? Well, we could use year 5, year 4, and year 3. And we recall with fondness from our forecasting study that it really is simple. It's an averaging technique, sum divided by number. So sum to add 1,950,000, 990,000, sum those and divide by 3. Sum divided by number. We're using 3 elements, so n is 3 in the denominator. The numerator is the sum of these 3 demand outcomes. We could do 5-period, MA5, 5-period moving average, using 990, 950, again, 1 million bats, 920,000, 875, so forth, sum divided by number. We could do a weighted moving average because there is an argument, and hopefully we picked that up from the PowerPoints and or one or more of the videos, that there was an argument, certainly among academics, but that we weight more recent data more heavily. So if, for example, we chose to do a 3-period weighted moving average, we would do the 990, the 950, and the million. But how would we weight these? And we remember the formula, the sum of the weights times the demands. The sum of the weights times the demands. Well, we have the demands. How would we weight these? We know from our study of weighted moving average that whatever combination or assignment of weights that we chose to use, a couple of things come to mind. One is that the total, the sum of those weights must be 100%. So if, for example, this were going to be 90%, which is something approaching ridiculous, well, then we had 10% left to distribute among these two. So it would probably be like 90%, 7%, 3%. Because again, the other underlying argument is we weight more recent data more heavily. Well, what's more recent? Well, year 5 is more recent than year 4, year 4 than more than year 3, year 3 more recent than year, you get the idea. And in the example we used, we said 50%, 33%, 17%. So if we did that, again, it would be 17% times 1 million plus 33% of 950 plus 50% times 990. That would give us our forecast. Now we notice 3-period moving average, 5-period moving average, 3-period weighted moving average. We already know from our study that the outcomes are going to be different. Which one is right? They're all right. Just applied a different technique. They're all forecasts. They're guesses, arguably educated guesses, whatever that means. But so we have forecasts. We'll know the actual outcome, the actual demand data number at the end of year 6, but we're at the end of year 5. We're trying to forecast that. The other thing we could do is we could use exponential smoothing, where that's kind of a weighting system as well. Remember alpha and then 1 minus alpha. We can equally weight things. We can put more emphasis on the demand, more emphasis on the forecast, the prior data, and work our way down that whole column. The last thing that we played with or we studied was linear trend line or, linear regression. So we could use that as our technique as well. So here's the point. The technique you choose for your final, for this portion of it, is up to you. It's not going to affect your grade necessarily one way or the other. I mean, unless the technique you choose, you do badly. So I might be doing something very simple like sum divided by number. Add them all up, divide by the number. That's my forecast. And that becomes the first piece of Betty's bats because we now have a production goal, a forecast number, how many we're going to make. Now, when we looked at PERT CPM, and in at least one of the videos, I made the comment that, there's a difference, and we look at the course as being OPPM, operations, production, project management. Well, in project management, there are different techniques. There's a lot of software today, but there are different techniques that we might incorporate. And we read a little bit about CPM, studied a little bit about CPM and PERT, program evaluation and review technique, critical path method. And so we centered in on the civilian version because PERT was historically more applied to military circumstances. So critical path. So we did CPM. And we used Frank's fine floats as an example. And if you go to Frank's fine floats and you studied that, then we realized that we had a priority of steps, of different things we had to do. And in Frank's fine floats, you had A through H, and in some instances, you had to make sure A was done before you could proceed to B. You had to make sure B was done, or A and B were done before you could do C, and so forth. But sometimes in Frank's fine floats, there were things that you could do incident to something else. So while I was working on C, perhaps I could also do D. And so that gave us, remember that whole array of boxes that seemed to be kind of discombobulated and disjointed. There were probably 3 or 4 things that were what the text and the slides referred to as slack time, free time. And then there were things that were critical. And recall with fondness that we looked at things like the duration of each activity, earliest start time, earliest finish time, latest start time, latest finish time without impacting the project. Because all of these things in the project were really related to what I've referred to periodically as the triple constraint: time, specifications, money. The triple constraint attached to every project, everything we do: time, specifications, and money. So we don't want to go over time, deal breaker, contract breaker, cost more money. Specifications, if we're digging a ditch and it's got to be 10 feet deep, we don't want it to be 4 feet deep. We don't want it to be 24 feet deep. Cost, $1 million, not $1.2 million, not $1.9 million. I mean, it'd be nice if it were 750,000 instead of $1 million, but that's probably pretty unlikely. So the triple constraint with us through everything. But the CPM piece was really more geared toward project. Project, build a bridge, build an assembly line, whatever it might be, build a hospital. Kind of a standalone thing. We're not doing a production. We're not building 10,000 hospitals. We're building 1, maybe 2, etc. Project. Production, so OPPM, production, is more like, and I used a couple of examples. One I suggested to you is like the, Ford plant or other automotive plants where there's an assembly line and the cars are built at different stations. Well, each station represents an activity, and once you have the queue filled, a finished car comes off the assembly line every, 5 minutes, 15 minutes, whatever it is. And I use the example of Liberty ships in World War II, where it was published that a finished ship came out of production every week. And so we look in askance and scratch our chin and say, you can build a complete ship in a week? Well, somewhat yes, somewhat no. I mean, can we start from cutting steel and laying the keel and have a finished ship ready to sail in a week? No. But when we do things based on activities and over time, well, once the queue is filled, we're really depending on whatever the longest individual activity is, because each time a ship is finished, 1 week's time, the next one has pushed, in a sense, everything forward to the point where I kind of used the car wash analogy. Think about what a car wash does. Car pulls up. Okay, activity A, we know what that is. You got to pay your money. But then what do? Well, in my experience, typically they take the high pressure water, high pressure washer, hand hose, and they take the big chunks of debris and dirt and whatever else off the sides of the car. Maybe spray the underside and the wheels a little bit. And then the chain grabs hold and starts to pull us through. And in the first station, now the car's already wet, but the first station is we get soaked. And then the next station is the brushes come down and they beat the heck out of the paint and finish on the car. Then the station after that, you get typically high pressure water to wash off the soap and dirt and debris and paint and whatever else, and so on and so forth. And eventually you get a big blow dryer that comes down, blows all the water off, and then it spits the car out the back end. Well, do they wait at the car wash for a car to start here and go there 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 and come out the back end before they allow the next car in? No. That would be like Frank's Fine Floats. We go through every one of these things, critical path, everything is critical. And when the car is done, then we start another. Doesn't work that way. It works more like a production environment rather than a project environment. In production, first car starts at whatever A is, this hose, well, pay the money, of course, then hosing process. And then from there it goes to B. But when it goes to B, there's another car coming into A. And when B goes to C, A goes to B, and another car lines up in A. And it's kind of like one pushes the next one. And in that environment, whatever the longest operation out of wetting and soaping and rinsing and air drying and all that, whatever the longest operation is how long it takes once the queue is filled for a car to come out the back end finished. That's what we're talking about with Betty's Bats. So even though you will put together a critical path, because I want us, euphemism for you, to put together a Frank's Fine Floats type outline for critical path, CPM, prioritizing the activities, etc., earliest start time, earliest finish time, blah, blah, blah. That's not in effect what we would really do for Betty's Bats. Part A, forecast, you need that number. Part B, CPM, excuse me, you need that number in as much as you have to schedule the activities, prioritize the activities, and in a project environment, you will have a number generated by this CPM, critical path method, but you're also going to have a number generated by throughput. I've mentioned that before, and I hope we did some of the reading and studying on that, because the third part of Betty's Bats is what we're actually going to do. So, for example, I forecast. I take this up here, and I come up, sum divided by number, I come up with 940,000 bats. The forecasting technique I did. So I've got to make 940,000 bats. I come down here to the part of CPM that we say, well, what are the actual activities or operations involved? Well, the first one is slugging. Now, again, there was a video for you to watch that highlighted some of this, and it's not the exact process because I simplified everything for us because we're not an engineering school. But slugging, we said, okay, so to take these big round bars of aluminum, first thing we have to do to be able to plug them into a lathe and turn them or put them into an extruding machine and extrude them. And you don't need to know what a lathe is or an extrusion machine is or anything like that. This is not NJIT. But the first thing we have to do is we have to have a slug, some length of whatever, 3-inch, 4-inch diameter aluminum bar. And the bars come in typically in 20-foot lengths or whatever, so they have to be cut into these shorter sections. That's what slugging is. And we're saying it takes 3 minutes to take this bar and cut a piece off. Slugging. So we make a slug. 3 minutes. From there, we go to, and again, this is not a completely legit, it's not entirely incorrect, but it's not everything that we would do. But just for our purposes, we go from slugging to a first extrusion. Well, extruding that slug takes 2.5 minutes. When we're done with that, we put it in a second machine to extrude it again, and that takes 4 minutes. And from there, we go to finishing, which takes 3.5 minutes. Now, in between all of these, there are handlings. What do I mean? Well, the slug has to be moved from the saw that cuts it to the extruder, from the first extruder to the second extruder, from the second extruder to finishing. Well, is that done manually? Do we accumulate parts and then move a big basket of parts using a forklift? Is this all automated where we use a robotic arm that takes it from the slugging and puts it in the extruding machine, takes it from the first extrusion to the second extruding machine? And so how are we doing this? Well, we don't know. And again, we're not an engineering school, so we're not playing with all of that. So all of that to say, we are adding 1 minute to our overall throughput, our per piece time to manufacture throughput. We're adding 1 minute to account for all of the handlings. So now think back to the car wash, and what we said is you wet the car, you put it on the chain, you soap the car, you high pressure rinse the car, you dry the car, and then you wipe the car. How long does it all take? Well, whatever the longest operation is, once we have all these cars lined up and the queue is filled with cars at different stages of completeness, once the queue is filled, we spit out a car every, whatever that longest amount of time is. So in our case, and this is the point to you, in terms of throughput, once the queue is filled, we spit out a finished bat. Betty's bats, we spit out a finished bat every 5 minutes. So now we know, CPM aside, because that would be the number if this were a project. We were making one bat. But in a production process, throughput is what we're concerned with. We spit out a finished bat every 5 minutes. Well, how many bats I got to make? 947,000 bats. And each one takes 5 minutes to complete. Well, I've got to get all of this done in a year. So let's break some things down. Let's start with a couple of generalizations. 52 weeks in a year, but there are really only 50 production weeks. There are 24 hours in a day and 40 hours in a typical work week, 5-day work week, The same thing like you and I might work, in a bank or wherever it happens to be. So we work 40 hours a week, but that's one shift. So one shift for a work week is 40 hours. Well, let's start looking at some of these numbers. 947,000 bats times 5 minutes per bat. That's a lot of minutes. It's a lot of minutes. What we start to find out is that we, in our environment here, are going to need 3 manufacturing plants, 3 factories, if you want to look at it that way. Each plant will have 6 production lines. There are 50 production weeks, 40 hours per week times 50 weeks, 1 shift, 1 line. So in other words, 40 hours per week times this 50 weeks. If we only did 1 shift, 9 to 5 kind of thing, and had 1 production line, 1 set of slugging machines, 1 extruder, 1 second extruder, 1 finishing station, et cetera, et cetera. So if we only had 1, do the arithmetic, or as Robert De Niro would say, do the math. We have 2,000 hours. 2,000 hours times 60 minutes is 120,000 minutes. Well, we got to make 947,000 bats, each taking 5 minutes. So multiply 947,000 times 5, or whatever number you came up with, doing whatever forecasting technique you choose to do the multiplication, break it down to minutes, and you find out that 1 shift and 1 assembly line or production line rather, that gives us 120,000 minutes ain't nearly enough to meet the production over 50 weeks, over a year. 120,000 minutes divided by 5 minutes per bat means we're only making 24,000 bats per shift per line annually. So if we did 3 shifts, typical morning shift, typical evening or afternoon shift, and an overnight shift, a midnight shift. So if we did 3 shifts under these circumstances, we would end up with 72,000 bats. We need 947,000 bats. 3 shifts, then times 6 production lines. Well, that only gives us 432,000 bats. But if we have 3 plants, 3 manufacturing facilities, 3 shifts, 3 plants with 6 lines each, production lines each, gives us a capacity of basically 1.3 million bats. Now, this year, based on our forecast, we don't have to do 1 million or 1.3 million. We end up, and again, using my calculations, for me, it was 947,000. So I can certainly accommodate that with this. And that's what we're doing as far as the third part of Betty's bats. So now we know what our targets are. But then we have the optimization problem, part 3 of Betty's bats, continued, because we said 3 plants, manufacturing plants, but then after the bats are made, where do they go? Well, we've got to store them someplace. So we have 3 warehouses. If you did the studying and the work and the tasking that I put out there, then you now realize this sounds very much like tropic sun. 3 citrus groves, 3 citrus processing facilities, each with different handling capacities, each with different distances. Oh yeah, this is just like tropic sun. What was our objective? Tropic sun was to minimize bushel miles. What are we doing here? We're minimizing bat miles. Let me stop share. I want to pull up one other thing. And because it's a short semester, and I don't want you to struggle too much, I do want you to learn. So I don't want to just give it to you. But while I will not post this, just like we set up tropic sun, we have Betty's bats. And we have plants 1, 2, and 3, and warehouses 1, 2, and 3. And the distance from plant 1 to warehouse 1 is 6 miles. The distance from plant 1 to warehouse 2, 19 miles. Distance from plant 1 to warehouse 3, 22 miles, etc. Well, what are the capacities? Well, each of the plants can produce 315,667 bats. What are the capacities of the warehouses? One can hold 350,000, one can hold 500,000, one can hold 450,000. Remember tropic sun. We had a non-negativity constraint. We had a less than or equal to constraint. We had an equality. Just like tropic sun, you have the same kinds of things here, except that the mileages are different. And the numbers in terms of capacities and production are different. But also, just like in tropic sun, you have embedded formulas. Our answer here, and again, our objective function, if we were to pull down solver, is to minimize. Minimize what? Minimize bat miles. But remember, our answer, this embedded formula. If we look here, embedded formula. If we look here, embedded formula. If we look here, embedded formula, you get the idea. So that if we were actually going to solve this and pull down solver, well, we know where our answer is going, our set cell, outcome cell, answer cell, right there. We know we have a non-negativity constraint. We know we have an inequality we're dealing with. We can use all or some of the capacities. We just can't exceed it. And then we have an equality. So our objective, minimize. Minimize what? Minimize bat miles. All right, I'm going to stop share. Let me close this. No, I am not posting this. Don't want to save. Stop share. Okay. So this is your final deliverable. This is Betty's Bats. I'm putting this out there to hopefully make things a little bit better for you, a little more understandable for you. I hope to be able to meet on Friday. We will not meet tomorrow, Wednesday, at our normal time. I'll send out a message to that effect because I doubt, I'm in the process of shifting some things and moving some things. So we will not have internet tomorrow. So I will not hold a session tomorrow. but I'm putting this out there because this should be all that you need to be able to resolve this. Remember, that's what you are tasked to do for your final deliverable. The production sheet that will end up looking like, let me just see if I have that here. No, that's that. No, let me see if, well, in contents, let me see if I have that up there. Let me just see for a second. No, I don't think I have that, but no. Okay. In contents on Blackboard, you have a sample of Betty's bats. It's PowerPoint, so that's what you're tasked to deliver. PowerPoint showing your forecasting and your results, all of the work, your critical path, including your diagram, earliest start time, earliest finish time, everything that you see in Frank's floats. You should have about 5 or 6 pages on that. You should have about 2 or 3 pages on the forecasting, and you'll have a few things on the final optimization. Now, likely you will take a snapshot or screenshot of your final optimization, the Excel sheet. You must also attach the Excel sheet with that, because obviously a screenshot is non-functional as far as me being able to get into it and see that you did the formulas and everything correctly. So in addition to the screenshot of the optimization piece, you need to have the Excel sheet sent over as an attachment as well. So you'll be sending 2 things, the PowerPoint and the Excel spreadsheet, to both of my emails, preferably, but certainly my NJCU email, not to the message function of Blackboard. You are sending your final work product to my NJCU email. All right, email me with any questions. If we need a private Zoom, I'll try and arrange one. I hope to be able to meet in Zoom on Friday. Let me just confirm that. I think everything should be in and functioning by then. Yeah, that should work. So we should be able to do Friday, barring disasters. But Wednesday we will not meet. Tomorrow we will not meet. Be well, have fun with this, and email me with any concerns that you have. Have a great day.